try that. Okay, now I'm recording. All right, so we were talking about the flag, and we said we have this realistic changing rate of change function, and there was a time in history where the flag was coming down, and it was coming down according to this rate profile as the soldier lowered the flag hand over hand. And we said we're interested in trying to figure out what is the exact net accumulation function for this rate function, and that would be the idea of how much you have, or how much the height of the flag. Okay, and so the first thing, what was the first thing we did? The first thing we did was we said, well, if it's a changing rate of change, it's very difficult, if not impossible, to figure out amounts of change if the rate is continually changing. And so we need constant rates, right? We need constant rates so we can apply dy equals mdx to work towards accumulation, right? Those dy's are little changes in the height, and that's moving towards accumulation. So we built a step function, which was our pretend rate function. And we learned two different methods to do that. We said that we could just eyeball, like, our best guess at the average rate in every interval. So that was like an eyeball method. And then last time we talked about, okay, how about let's make each constant rate, we'll get that constant rate from the rate at the left side of the interval. So we'll pick off the actual rate at the left side and let that be the constant rate the whole way. Even if that was a horrible estimate in that interval, we're just going to use that one rate at the left side and let that be the constant rate the whole way. So, for instance, in this interval, the constant rate was this value right here, so we let that be the constant rate for the whole interval. And this was our pretend rate function. This is our pretend rate function. And from the pretend rate function, we said, okay, now with that pretend rate function, we can generate an accumulation function. So going down at a constant rate, but then as soon as you move to a new interval, you're going to head down at a different constant rate. So you're going to have this like piecewise linear function. And so what is this function doing? It's tracking the net change in height of the flag, in this case since 0.6 seconds after we started lowering the flag. And so, moving back here, and we looked at a particular example of that. We said, okay, say right here. Yeah, actually this is what it was, 2.15. We said, so this is at this point right here, at this time, 2.15. How would we calculate how much the height has descended since 0.6 seconds? Or in other words, what is the net accumulation of height? A of 2.15, which would be this, something like this right here. What is this value, right? So how much has the height descended at 2.15 seconds since 0.6 seconds? And so then we looked over here and we said, okay, well, we said, how would we do that? We said, well, we would add up all the accumulation from the completed intervals, right? So we've got constant rates, so we can use m times the change in x, m times the change in x. So we accumulate those changes. So m1 plus delta x plus m2 delta x plus m3. So this was all the accumulated change from the completed intervals. So in this case, there were 4 completed intervals, plus a little more change, right? A little more change from the current interval. So this would be m5 but not delta x, but dx. Dx is how far we are into the current interval. So this is our delta x of 0.35. Dx is how far we've gone into the current interval. So we said we can generalize that. The sum of all the change from the completed intervals, we can use this symbol, which just means sum, right? Sum up all the m delta x's. So we say mi, so I goes from 1 to the number of completed intervals. So I is 1, and then I is 2, and then I is 3, and then I is 4. We're going to sum all those up, plus, and that's our r of x, right? That's our r of x function, that blue approximate rate function. And then we have the last rate for the current interval times dx. So the amount of accumulation is the sum of completed intervals, the sum of the accumulation from completed intervals, plus a little more accumulation from the current interval. And that's kind of where we left off, so that's getting us up to speed. And so how about this approximation? Good or bad? How about this function here? So let's take it. So this approximation for the net accumulation of height is based on this blue step function, our pretend rate function. Good or bad approximate accumulation function?
Terrible.
Pretty bad, right? Because look at this, the rate function is not doing a great job mimicking the actual rate function. Our pretend rate function is not doing a good job pretending, right? It's not a good simulation. So the question is, we want exact accumulation. We want this to be right. Not a bad, crude approximation, but we want it to be right. So what can we do to make it better?
Increase the size of delta x.
Right, so if we make smaller intervals, then this rate function will mimic the real rate function better, and our approximate rate function will likewise be better. So let's do that. I'm going to hold on to this approximate rate function. That was for 0.35. Okay, and so I've kind of put it faintly. So this is the one before, and now I'm going to make delta x. I'm just going to click something here. So now delta x, the new delta x is 0.1775. If you can read that right there. So before it was 0.35, now it's 0.1775, and let's see what happens. Ready? Here we go. Here's time going by. And so now the interval width is smaller, and the rate function is, the pretend rate function is a little bit better. So do you see how this, now the blue function with the smaller intervals is kind of doing a better job of mimicking the real rate function? And so now this dark is this is our new approximate rate function. You can see how it's much different than the original. So the original is the fainter one. That was the one we had before for delta x of 0.35. Now our delta x is 0.1775. And how about this approximate rate function? Better or worse?
Slightly better.
Slightly better.
I have a question.
Sure.
So how did the new delta x determine what the rate will be? Because first it was like the average. So how are we to...
No, it's always left. So we're always doing, we're using the left method now. So the very first time we did this, like the second day of class, we eyeballed averages. Then we said, let's use the left method where we just take the rate from the left side of the interval and let that be the constant rate for the whole interval. So now I'm just doing that. I'm still doing that with a smaller delta x. Does that answer it?
Okay, so it's still left hand.
Yeah, we're still, this is, yeah. So yes, so for a systematic, kind of more systematic way, we're going to keep doing left hand. So like, here's my intervals. There's 1, there's 2, there's 3, So here are my new intervals. So for this interval, left side. For this interval, left side. For this interval, left side. Do you see it?
Yeah, that makes sense. Thank you.
Yeah, sure. Now, in your homework, make sure you read carefully. We have two different ways of doing it. So if the homework is asking you to build a approximate rate function, read the instructions carefully. Is it talking about, is it talking about building it by the eyeball average method, or is it talking about building it by the left-hand method? We've done both. And so the homework could ask for either one. So read carefully, okay? All right, so we're getting better. We're getting better, but we want to do even better. Okay, I'm gonna erase some things here. That's fine. Okay, so I'm going to hold on to this one now, which was 0.177. Okay, and now I want to make it even better, so that means smaller. So here is, I can't read that. What does that say? 0.0395. So now our new delta x, so this was from the delta x of 0.177. And now we have a new delta x of 0.0395. All right, so let's check it out. What happens when we use this delta x and let x vary? So we're looking at variables vary, right? So we're going to let x vary. So, and let's turn off this for a second. Let's watch the rate function. So here's the rate function with this new smaller interval, 0.0395. How's that doing mimicking our actual rate function?
Pretty good.
Yeah, pretty good. So now these little, because the interval is so narrow, these little steps using the left-hand method are now starting to really match the curve. Okay, so let's watch the approximate accumulation function. That's the old one, right? That's the 0.177 delta x. So here comes the approximate accumulation function for delta x of 0.0395. So is the new approximate accumulation function the same as the old one? Is it the same? It's a little bit better, but we can still see daylight between them. You see this? There's still places where you can see how these are still approximations, right? It's still approximation because they're distinctly different, right? Well, they're really close, but they are different still. Okay, so but we want the best, and we have the technology to do the best, and the best is exact, right? So exact would mean just keep making those intervals smaller, so like super small. So we're going to do one more time, and I'm going to hold on to the 0.0395. So there's the 0.0395. And now I'm going to go what we're going to just call like essentially really, really small, which is 0.005. So now the new delta x is 0.005. And we'll watch them both at the same time. So we're going to watch the approximate rate function emerge and the approximate accumulation function likewise be generated. So here we go. So check out the rate function first of all. This is still This is still a bunch of little steps, a little horizontal steps. So let me turn the rate off here. So now I turned off the original rate. So now I'm just showing the pretend function for the super small 0.005 delta x. And if you squint your eyes, you can't even tell the difference now anymore. Okay, and then what about over here? Can we see any difference between a delta x of 0.0395 and 0.005? So really none, right? So we really can't see the difference anymore. And so we basically say, okay, when is it exact? Well, it's exact when we can't see the difference between approximations anymore. Making delta x any smaller from here, it won't make a difference. It's not gonna make it really any better for practical purposes, right? For practical purposes, smaller delta x is not gonna make it any better. So we get to a point where we say, quote, it's small enough, right? It's small enough that these approximations don't deviate from each other anymore if you keep making it smaller. It's not going to improve any more if you keep making it smaller. So the approximations we got for these two essentially the same, so we call it a day. We say we did it, we got to exact accumulation. Okay, and so what happens now is we've got our exact net accumulation function. So our function, so this function, we said AX so I'm going to rewrite this one a little bit nicer here. Okay, so we said A of x equals sum of, this is our approximate, right? R of x delta x for all the completed intervals. We're summing up all the change for the completed intervals plus a little bit more change for the amount we've gone into the current interval, right? So that's dx. So what happens when delta x is super, super small? Well, then like that current interval really is just kind of becomes like the last completed interval. There's kind of like, there's really no distinction between a dx and a delta x anymore because it's just so small that there's no distinction. So this, as delta x gets very, very small, this just becomes like our last completed interval. Can you buy that? And so then our exact height, net accumulation of height, then we have new notation for this. We have a new kind of compact notation. Instead of writing this, the approximate accumulation function, does anybody know how what the sum becomes? Integral. Okay, so we're going to integrate, and now our delta x's are so small that it's like we're taking every single rate, like we're every rate, and so we're going to use, so our bits of change are based on like every single rate, and then times these little teeny changes in each interval, for each interval. Okay? And so we're going to start at A. So this was our 0.6, and we call that value A, our starting value of accumulation, up until x. But then for any given x, right? So for any given x, we need to sum up all the little changes, and so we have to change from A to x. So we're going to select a new symbol that means all the x values from A up to the current value of x. So we need a new symbol there. That is still an x value, but we can't use x because x means like where we're accumulating to. So when our delta x gets small enough, this approximate rate function, we have new notation for exact rate function, the exact accumulation function, and it's this. We're accumulating, it's the net accumulation from A up to X, and that's by summing up, right? Summing up all the changes as X varies from A to X. And so then this T value is the X values varying from A up until X. Okay, and so now we're very, very close here to how much we have. What would how much we have be in the situation? How much we have would be height of the flag. So this was net accumulation of height. Now we want what's called total accumulation of height. That would be total accumulation, and now this is the actual height of the flag. All this time we've been talking about how much change in height since a certain time. Well, what we really want is how much we have in terms of like what is the height of the flag? So what's the one step we need to get from net change to actual height of the flag? That would be our h function. What's the bridge from changes in height? This is telling us how much the height has gone down at every moment. And now I want to make one adjustment to that so that it's actually tracking the height of the flag. What would I need? How would I need to adjust this so that it's actually giving us the height of the flag? Anybody? Can you also? What's that?
Could we add an initial?
Yeah, right. So if we took all these changes in height and added what the height was at 0.6, right? If this instead was the height at 0.6, we moved it up and moved all these net changes up the same amount likewise, then we'd have the height of the flag. Does that make sense?
So is A of H basically making the net change?
This one.
Yeah, that's the height, correct?
No, that's not the height. That's how much change in height since 0.6, right? So at 0.6, this function,
Okay.
yeah, at 0.6,
That
this,
makes a lot more sense.
yeah. At 0.6, this function gives a value of 0, right? There's been no change in height since 0.6. So then that's why all these values are negative, because it's telling us how much the height went down at a certain x value, how much it went down since 0.6 seconds. So what we want to do is we want to get the right height at 0.6 and move all these y values up accordingly, and that'll be the height of the flag. So it'll look something like this. Can you see that? So now, if I knew the height at 0.6, what it actually was, right here, and just added on that height at 0.6, then from that height at 0.6, we'd have the net change, and we'd be tracking the height of the flag now. So what do we want to do? So what is the height at 0.6? It is h of, and also, so I wrote a here, h of a. It's the height at our starting value. And now we're going to add on all the change since A. An animal has joined me. That's my cat. Okay. So there it is. We made it, right? You know how fast a quantity is changing at every moment? The actual rate of change of height of the flag. You want to know how much of it you have at any moment, the height of the flag. So we've arrived. Given the actual rate of change or how fast it's changing at every moment, in our case height, this function now gives us how much we have at every moment, or the height of the flag.
Professor, I just realized the video isn't being recorded right now.
Yeah, I'm using a software instead of Zoom to record, but thank you.
Gotcha.
Yep, thank you very much. Okay, any questions? So we're going to review the principles, but like any questions on this development, how we got from the pretend rate to the approximate rate, and then we looked at smaller and smaller delta x intervals until it didn't matter anymore, making it any smaller didn't matter anymore, and we just basically got the same thing. And then we called it a day and we said, okay, that's the exact net accumulation function, and we said we have a different notation for that, integral notation. And then we said we were one easy step away now from the height of the flag, which is just add the initial height to all those changes. And then that's going to track now the actual height of the flag as time goes by, right? As x increases, we'll have the initial height plus the net change since that initial time, and that'll give us the height at any time x. Any question?
If we change the delta x to be really small, is that what we put in for t?
No, so the reason that we did t was x is like, it's where we're accumulating to, right? So we start at a and we accumulate to x. But in order to do that, we need all the x values in between. So t varies, t is an x value that varies from a to x to get that amount of accumulation at x. Does that make sense?
Oh, yeah, because when we would like solve the integral, we'd be like RH of x minus RH, like we would.
Right. Yeah, the x would come back into it.
Oh,
but
okay.
if we put x
okay.
here, then say h of 4 would only use it would be r sub h of 4. It would be using a constant rate of 4 for the whole way. We don't want that. We want the changing rate from the starting point to 4. So we use a different symbol to represent how x changes from a to x. We don't want to put x there, because then, like I said, h of 4 would only use one rate, the rate at 4, for all the values from a to 4. So it would just be accumulating at one constant rate rather than the changing rate profile that we want. Okay, so let's summarize the principles, and as we do that, we've seen a progression of functions here. That's really important in this journey of, you know how fast it's changing, you want to know how much you have. So we want to review the principles and highlight this progression of functions that made this possible. So here we go. So, you know how fast the quantity is changing every moment? You want to know how much of it you have at every moment. Can you all see my PowerPoint?
Yes.
Thank you. First principle, constant rate of change. 60 miles per hour, a constant rate means given any change in our independent variable, in this case hours, we know the variation in distance. And we need that because remember we made our intervals really small. We didn't keep our interval with at 1, right? Our delta x needed to get smaller and smaller. And so for those smaller and smaller intervals, we needed to know what the dy's were, right? So constant rate of change means for any change in x, the corresponding change in y is that rate times the change in x. Okay, principle 2, we talked about a net accumulation function, and it gives the amount of change in a quantity for any value of x, and the rate of change is known. Okay, so principle 3 is where our progression of function starts, changing rate of change. Realistic rates are often changing rates. So this is in the progression, this is number 1. And that's our exact, this is our exact rate function. So we'll call F, F1, function 1. Principle 3 is about function 1, the exact rate function. You know how fast a quantity is changing at every moment. That's what we're given. That's what we have. Okay, principle 4, pretend rate function. So we're going to mimic the rate function, but with constant rates. I don't have my pretty picture there. I'll draw it. So we did right, so I've got these intervals here. And so we made a pretend rate function. I'm sketched it with the left method here. And so that pretend rate function is our function number 2. So from the exact rate, we have approximate rate of change. We call that R, right? F1 was like R of F. The exact rate, R of F, function number 2, R. And that's the piecewise step function. That's the pretending to be the real rate function, but with constant rates. That's R. Okay? The next principle, approximate net accumulation. This is function 3. Function 3, approximate net accumulation function. That's what we did last time and today, right? So we out of that pretend rate function of constant rates, we said add up all the accumulation from the completed intervals, m times change in x plus n times change in x, plus a little more accumulation from the current interval. And this was what? Using our approximate rate function, right? Using R. So we got RF. So right up here, we got RF to our approximate rate step function to our approximate accumulation function. And then what? Yeah, so by making the intervals small, and we said small enough, you make them smaller and smaller until there's no difference anymore. Making it smaller won't make a difference. And so then the approximate net accumulation function, this thing, as delta x, this means gets really small, gets close to 0. Our approximate becomes exact, and this sum notation becomes integral notation. So that's A sub F, exact net accumulation. And finally, exact total accumulation. So this is tracking changes since A. If we have the total amount at A, then by adding that on, we get the total. So add the previously accumulated amount to your net accumulation to get a total accumulation. And here we are, how much you have at every moment. So that's F. So again, you know how fast a quantity is changing at every moment. You want to know how much of it you have at every moment. So this is our golden function that answers that solves that problem, answers that question. And now this applies to any quantity. All you need, so what do you need? You just need the rate of change of that quantity. If you have the rate function for that quantity, then you can you can write down the exact total accumulation for that quantity. Okay. Any questions? All right, very good. So let's just look in detail at so this whole journey has been about what an integral is. So now we see that an integral is a function that gives net exact accumulation of some quantity when you know its rate of change. Okay, so from now on, whenever you see an integral like this, whenever you see an integral expression like this, we want to think of this as our approximate, right? So that we spent all this time this week coming up with this idea of this approximate accumulation function, because it's really the guts or the machine of integral. So we want to, whenever we see an integral, we want to think of this thing of summing up completed intervals plus a little bit more in the current interval. But this now has the super small delta x. So we want to think of the integral as our approximate accumulation function with the smallest value of delta x, so that the very small size of the completed intervals makes the partial interval essentially the last completed interval. So it's kind of like the difference between dx and delta x is like there's really it's like negligible difference. So it's kind of like they're all dx. So how are they the same? So where in both of these do we see how fast the quantity is changing? Where in each of these? So in both of these we see how fast the quantity is changing. Where do we see that? Rate, right? Rate. So this is the exact rate of change, and this was our approximate rate of change. Okay? Where do we see how much of it we have? So where do we see in both of these how much we have? Okay, that's just the value of the function, right? This is this net accumulation. Or we know it's like one step away from how much we have, right? Net accumulation is just that one little step away from how much we have at every moment, okay? Which is found by summing up. Where do we see the idea of summing in both of these? Right, so the integral symbol or the Greek sigma are both talking about summing up bits of change, right? Summing up bits of change. And what are the bits of change? What is it that we're summing up? So where, this is maybe the most important question, and it's the one that students struggle the most with. Where in each of these do we see a bit of change or a little bit of accumulation?
Would be the starting variable in the summation, and then the a to x in the interval.
Not quite. So we're talking about, so how did we calculate a little bit of change for, like, say, one interval? How do we calculate the accumulated change over one interval?
What are x? Oh. Okay. Sorry.
That's dy, right? dy. What was dy equal to? dy equals?
Would it be the r of f of t dt?
Right. mdx, right? This is how we calculated a little bit of change for one interval. And then we're going to sum those all up. So this is kind of like the most important thing right here. This is a bit of change. There's our mdx right there. It's multiplication. It's the current rate times a little bit of change. And we're summing all those up from a to x. Likewise here. This was our constant rate over the interval times the width of our interval, delta x. That's what gives us a little bit of accumulated change. And then the accumulated function is where we keep track of the running total, right? We're adding those bits and keeping track of all the accumulated change, the sum total, up to the current value of x. So So that's the way you want to think about an integral from now on. So could integrals mean area under the curve? Yes, they could. But to understand that, you have to understand that they don't mean area under the curve. What they mean is the net accumulation of any quantity. And then we could say, all right, we're interested in area, and then we can apply an integral to help us find area. But it's not intrinsically area. It's intrinsically the net accumulation of any quantity that we choose. Okay, quiz time.